Hello, today what we'll be doing is we will start by analyzing what the heaviside function is. Well, more exactly, we're going to review what the heaviside function is and all its implications, and then in the end, we will have our big reveal about how heaviside functions can be used to write down piecewise functions. So let's begin. First, what we are going to do is we are going to give the heaviside function, or as we're going to be referring it to, h of x, a meaning, or we're going to define what this is. And simply, h of x, or the heaviside function, is a function which is 1 when x is greater or equal to 0, and 0 when x is smaller than 0. And so we have it right over here. So when x is smaller than 0, everything is 0. Then once x becomes 0, it becomes 1, and it continues. So it continues like this forever. And a good way to think of it, as well, as you can think of it as a light switch, right? So you have your lights off and everything is dark while the light switch is off. And then when you turn it on, so when you have your, I'm going to try to draw a light switch for fun. So here, if we have our light switch off, the room is dark. But as soon as you turn it on, the room becomes bright. And so that turning on, you can kind of think about it as the x becoming 0. Great. So in and of itself, heaviside function is pretty simple. Now what we're going to do is we're going to look at some of ways to use or manipulate the heaviside function. So the first way we're going to look at it is we're going to look at it if we use it with an f of x. So if we put another f of x into it, let's see what happens. So if we have f of x times h of x. So what's going to happen here is, again, it's going to be a piecewise function where you're going to get f of x when x is greater or equal to 0, and h of x, or not h of x, sorry, and 0 when x is smaller than 0. And the reason for this is because the heaviside function, as we know, is defined as 1 when x is greater than 0 or equal, and 0 when x is smaller than 0. So if x is smaller than 0, then h of x is going to become 0. And then no matter what f of x is, 0 times f of x is 0. On the other hand, if x is greater or equal to 0, then h of x is 1, and 1 times f of x is f of x. And that's why this is the way it works. Now, on the other hand, we have h of f of x. And in this case, what we have is it equals to 1 if f of x is greater than 0, greater or equal to 0, and 0 if f of x is smaller than 0. And again, you can think of it the same way. So h of x is 1 if x is is greater or equal to 0, and 0 if x is smaller than 0. So now instead of x, what we have is f of x. And so if f of x is greater or equal to 0, then we're going to get 1. And if f of x is smaller than 0, we're going to get 0. Perfect. Now what we're going to do is we're going to look at how the h of x function actually changes. So here it is. So let's start with a simple one, relatively. So we have h of x minus a. So h of x minus a is going to equal to 1 when x is greater or equal, when x minus a is greater or equal to 0, and 0 when x minus a is smaller than 0. And you can kind of think of the reason I'm doing this is it's the same way as you would do for piecewise defined function or an absolute value. So for instance, if we had absolute value of x minus 5, right, then this would be defined as x minus 5 when x minus 5 is greater or equal to 0, and negative x plus 5 when x minus 5 is smaller than 0. And then you can simplify it. So here you could just see that x is greater or equal to 5, or x is smaller than 5. And so over here, what we can also do is we can simplify it where it's going to be 1 when x is greater or equal to 0, and it's going to be 0 when x is smaller than a. And this makes sense just if you think about it. If this is bigger than a, then something bigger than a minus something minus a, it's going to give you something bigger than 0. So therefore, you're going to get a 1. And if not, you're going to get a 0. Perfect. And now we're going to look at 1 minus, and actually, before we move on, I will quickly draw this for us. So let's get our drawing tool. So over here, over here, you can kind of think of it as we're just shifting it. If you know how to move your functions, I forgot the exact term right now, but you can kind of think of it like that as well, because we have minus a, we're going to move it to the right a spaces. So over here, it's going to be 0. It's going to be 0 until we reach a. And at a, it's going to become 1. And then I'll just add our indicator. So over here, it's a. Then over here, it's whole. Here, it's filled in. And it's continuous on both sides. Now, let's take a look at 1 minus h at x minus a. And over here, what we can do is we can analyze it both in terms of moving our function, and then in terms of how this would look like if we do it mathematically. So let's start with the mathematical approach, or the quote-unquote method. So what we can do is we can go over here, and we can say 1 minus 1, because h of x, we know that we know that the two outcomes for h of x is 1 or 0. So we know it's 1 minus 1 when x minus a is bigger or equal to 0, because that's what we have in the heavy side. And then 1 minus 0 when x minus a is smaller than 0. So again, we can just simplify this over here quickly to x is greater or equal to a, and x is smaller than a, and there we go. And then if we, how's it called, simplify our left side as well, in the end, we're going to get 1 when x is greater or equal to a, sorry, it's 0 over here. I just miswrote. 0 when x is greater or equal to a, and 1 when x is smaller than a. And you can think of this as the exact opposite of what we had before, right? Before, what we had is that it would be 1 when x was greater or equal to 0, but in this case, we just put a, and then, or 1, and then 0 when x was smaller than 0, but in this case, it's a. And you can kind of think of this as an off switch. So if it was the opposite, that when you had your switch turned off, the light would be on, and when you had your switch turned on, your light would be off. As weird as that sounds. Now, graphically, you could think of it like this. So if we draw our axes quickly, there it is. So graphically, you could think of it like this. So if we just draw it, our original function, it's going to look something like this, right? We already saw it. So there it is. It's going to have a hole at 0. It's going to be filled up top here, and it's going to continue. Then, if we start doing our transformations, they're called transformations of function, what we're first going to get is negative h at x is going to flip it on its x-axis, or across its x-axis. So then it's going to become something like this. It's going to look like this. If we were reflected in our h-axis, it's going to look like this. So it's going to be filled in here. And then over here, you're going to reflect it. So this is -1 now. And there you go. Then we start doing our other transformation. So the first one we can think of is it's going to shift 1 up because we have a +1 over here. Then minus a is going to shift it to the right a. So in the end, what we're going to get is a function that looks like this. If we shifted 1 up by 1 and to the right by a, we're going to get something like this. So we're going to have an open hole over here. And then at a, it's going to go and become 0. There it is. And this is at a, which is what we got from our math kind of results as well. Finally, we're going to face our final challenge before we actually reveal how cool the heaviside function is. And so the way we're going to do that is by looking at h of x minus a minus h at x minus b. And I'm just going to give you a couple of seconds if you want to pause the video and think about this yourself before I show you what this actually is. And hopefully whoever wanted to stop the video paused it and had it. So a quick assumption I did forget to mention here is that we assume that a is less than b. And so now let's start. So what we're going to do is, because we do know that this is a piecewise function, what I'm going to do is I'm going to analyze all the case scenarios that we can kind of get depending on what our x is. So we're going to have our first case. And in our first case, we're going to get that x is smaller than a. So if x is smaller than a, and we can kind of think about both of these if you remember. So if x is smaller than a, then h at x minus a is going to give us 0, and h at x minus b is also going to give us 0. And the reason for this is because I hope you remember, if you go back and you see how h of x minus a looks like, it looks that if a is smaller, if x is smaller than a, then you're going to get a 0, and if x is larger or equal to a, you're going to get 1. And because a is smaller than b, it would be the same thing here. Okay, then we're going to have our case 2, and in our case 2, what's going to happen is that we're going to get a is smaller or equal to x, or x is smaller or greater than a, or smaller than b. And in this case, what's going to happen then is that h of x minus a is going to be equal to 1, and h at x minus b is going to equal to 0. And finally, our case 3 is going to be, oh, and in this case, it's like that because if a is greater, x is greater or equal to a, this one's going to equal to 1, this one's going to be equal to 0. Hopefully kind of self-explanatory, not try to go back and just actually write out what h of x minus b is and h of x minus a. Finally, we have if x is greater or equal to b, and then both of our functions are just going to have h of x minus a is going to equal to 1, and h of x minus b is going to equal to 1 as well. And so what I did here, just to re-explain quickly, is I kind of took both of my functions in that you can kind of see embedded in here. You can see this one function and this another function embedded in here, and I just split them off and said what would happen to them in each of the 3 cases of a. And now if we look at it, so when x is smaller than a, we're going to have a result of 0 minus 0 when x is smaller than a. And we're going to get 1 minus 0 when x is bigger or equal to a, but smaller than b. And then it's going to be 1 minus 1 when x is greater or equal to b. And then if you look at this further, you can see that this over here equals to 0, this over here equals to 1, and this over here equals to 0. And if we were to draw this, you can maybe get a better understanding, but it's what this is called is an on-off switch, because your function is going to be on, then you're going to turn it on, it's going to go 1, and then you're going to turn it off again. So if we draw a function right now, what it's going to look like is it's going to be 0. Then at a, it's going to turn on. You can kind of think of it, it's going to go for a while, then it's going to turn off. There you go. At B, it's going to turn off. So it turns on when it reaches A, it becomes 1. Then at B, it turns off. Cool. Now we have all our building blocks to finally go and look at the final expression, where how we can use this heaviside function to define different heaviside functions. How we can just define different, not heaviside functions. What I meant is to define other piecewise functions that we could have. So the piecewise function that I'm going to use on this example is f at x is equal to x cubed, where x is smaller than 0, x when 0 is smaller than x, bigger than 1, or bigger than 0 but smaller than 1, x squared when x is larger or equal to 1. Okay, so now what we can try to do is we're going to try to write this function down only using heaviside functions. So first, what I'm going to do is I'm going to say x cubed, so f of x, is equal to x cubed when x cubed when you have 1 minus h of x. And if you think about this function is going to be on until x reaches 0, and then it's going to turn off. And what do I mean by that? So I'm just going to write this in black quickly. So this function is going to be on until 0, and then at 0, it's going to turn off. And what do I mean by that? Well, if you think of this function, right? So we have negative h of x, you're going to flip it, and then you're going to push it 1 up. What's going to happen is that this function is going to be 1. This function is going to be 1 until it reaches 0, and then at 0, it's going to become 0. And when you have 0 times x cubed, it's just going to become 0. And so this x cubed is only going to be present until you reach 0. At 0, it's going to stop being present. Then what's going to happen is we're going to add to it our second function, which is x. And here we're going to use our on-off switch. So x times h of x minus h at x minus 1. And so the reason this works is because h of x is going to be, if you remember, this is our h at x minus a minus h at x minus b, and the a here is just 0. And so this is going to be off until while you have h of x, while x is equal smaller than 0. At 0, this is going to turn on, and it's going to go to 1, at which point it's going to turn off again. So again, this function will be 1 between x is bigger or equal to 0, but smaller than 1, which is actually exactly what we want. As soon as x becomes bigger than 1 or smaller than 0, we don't want to see this x. So all the time that x isn't between 1 or 0, this is going to be 0. Therefore, the x won't really be there. Okay? And finally, what we're going to do is we're going to say plus x squared, and we're going to have h times x minus 1. And x minus 1 here is because that just means that our h of x function turns on or becomes 1. It becomes 1. Becomes 1 when x reaches 1. And so what are we going to see here? So we're going to see that while x is smaller than 0, this function is going to be 0, and this like not this function, this part of the function is going to be 0, and this part of the function is going to be 0. So only x cubed is going to be there because x cubed times 1 is x cubed. Then when x reaches 0, this part of it will become 0. This part of it will become 1, but this part of it will still stay 0. So all we will really see in the function is going to be x. Finally, when x is bigger or equal to 1, this is again going to become 0. So 0 times x is 0, but this is going to become 1. And so we will see x squared. Now, there's an easier way to visualize this, and we can see this way if we open up the brackets. So if we open up the brackets, what we're going to get is x cubed minus x cubed hx plus, so we're going to open up the brackets here, 8 times h of x hx minus 3, minus x h x minus 1 plus x squared hx minus 1. So now we're going to group like terms, and I'm just going to underline it so you can clearly see which terms are alike. Choose blue. So these terms are alike because they both have hx minus 1, and these terms are alike. So then what I'm going to do is I'm just going to factor out those things now. So we're going to get x cubed. X cubed plus, and then in brackets, we're going to get x minus x cubed times h of x. We just factored out h of x there. Over here, we're going to get plus x squared minus x times, okay, that's terrible, minus, okay, there you go, minus x times h at x minus 1. So then what are we going to see? We're going to see that you're going to have x cubed. So x cubed is always going to be there. Then when this h of x becomes 1, because it's going to be 0 until x becomes greater than 0. So when x reaches 0, to be more exact, h of x over here is going to become 1. Before that, it's always going to be 0. So when this becomes 1, x minus x cubed is going to start kind of coming into play, or it's going to turn on. And at that point, when this comes into play, if this is 1, x minus x cubed is going to join in, because before that, this was just 0, and so 0 times x minus x cubed is 0. But once this becomes 1, you're going to get x cubed plus x minus x cubed. And so these x cubes are going to cancel out, and then only x will appear in our function. This part of the function won't activate until x becomes greater or equal to 1, because this is x minus 1. So then when x minus 1 finally comes into play, then what will happen is that x minus 1 will become 1, and then x squared minus x will start being there. And then this x and this negative x will cancel out, and then you'll finally get x squared going into play. So in essence, if we just repeat, we're going to get x cubed while x is smaller than 0. Then at x being equal to or greater than 0, this part of the function will become, so this h of x will become 1. Therefore, what's in these brackets will kind of go into effect. Therefore, what we'll get is x cubed plus x minus x cubed. X cubed and x cubed will cancel out, so we'll be left with x. Finally, when x becomes greater or equal to 1, this part of the function will get into play, and then we'll get x plus x squared minus x, but this and this will cancel out, so all will be left with x squared, which, if you take a look, it's exactly what we had in the beginning. So, perfect. Cool. And that's how you would express a piecewise function just based on heavyside functions. Hopefully this helps, and good luck.